Wonderful. I'm super excited to resume our Human-Centered AI Masters webinar series. And what better way to start our new series, which is Meet the Instructors, meet your lecturers, meet the professors who will be teaching you AI Masters, where we have strong focus. We're putting in a lot of effort into how to build reliable, robust, and reproducible systems that also secure and are private, that manage your privacy and security in an effective manner. Obviously, it's a journey in which we are trying to build a master's program that enables master's students to actually learn not only how to build awesome machine learning and deep learning models. I guess the last 10 years, this is something all of you have kind of understood that this is where the direction is. All the big and small companies, large and small governments, they're all focusing into the advanced field of artificial intelligence, be it computer vision, be it language models, and looking into government or in public sector or commercial sector. So it's a very fantastic field. But now is the time to also start designing systems that are preserving your privacy, ensuring and safeguarding your bias, and understanding the bias, not safeguarding bias, understanding the bias. So again, long story short, I think it's better to, you've heard me talking about it for the last couple of years, but it's better to start looking at some wonderful researchers and teachers at the universities where we have this wonderful human-centered AI masters, and to see what their experiences are, how are they putting that into practice, and how are they going to teach you, because these are those wonderful people who will teach you the masters when you graduate from these universities. So I have with me Gergely Ács, and Gergely is an associate professor at BME University, one of our consortium partner members in the Human-Centered AI Masters program. And I'm really excited to introduce you to him. But Gergely, why don't you tell us a little bit about yourself so people know who you are?
Yeah, thank you for the short introduction, Terry. So I'm from the Budapest University of Technology and Economics, and here I am teaching basically privacy issues about anonymization, machine learning, and also security of machine learning. So this is what I'm going to focus on my talk today. And I finished my PhD like almost 10 years ago, so it was a long time ago. And then I did my postdoc in INRIA in France, and then I started to learn on privacy. At that time, anonymization was a very hot topic, and still nowadays, a lot of people are working on that. But now I gradually shifted toward the machine learning, and nowadays I'm working primarily on machine learning, basically.
Awesome. I also saw that you did a postdoc at INRIA. Those guys do a lot of wonderful work. I know a bunch of researchers, and I know Jan LeCun also goes and teaches there occasionally or giving guest lectures. So it's a wonderful research institution in France, right?
Yeah, it's composed of several centers around France. So there are in Paris, Nantes, Lyon, Grenoble, and I was in Grenoble. And they are very strong in machine learning and all the statistical methods. But I was particularly involved in a team which was working on privacy and different privacy issues, privacy of Wi-Fi technologies, tracking, advertisements, and anonymization.
Awesome. So great. So just back, taking the mic back before I give it back to you, Gergely. You have a wonderful presentation. You and I spoke at the background, and I'm really excited to learn from you. All the things that you've done in your past in your career and how you want to put that into practice by helping students learn what you have learned and practiced. So for the rest of you folks, just simple housekeeping. You can ask us questions. You can pose questions immediately as well. If there's any question you have around your anxieties around, hey, what is this AI master's program? Which universities are organizing it? Any basic questions or intermediate question or even advanced questions, go ahead and ask us here. You can post your questions immediately, and I will make sure that they get answered by us. And just to give you a bit of an understanding, we start the program, the master's program was already started at the university in Hungary, and the three universities in Ireland, in the Netherlands, and in Italy. They will be starting in September 2022. So there's still time. I'm sure people are already enrolling. If you have any questions, just go to humancenteredai.eu. That's where our website is, but the link is here, and you can just, if you just search Human Centered AI Masters, European Union, European Commission, you'll find it. If not, ask me questions, ask my colleagues questions, and we'll answer you. So with that, Gergely, I'm going to share your screen. I believe you have a presentation. Let me just put it back, adding this stream. And there we go. Go ahead, Gergely. Very excited.
Okay, thank you. So I hope everybody can see it. So I prepared with a talk about trustworthy machine learning. It's a kind of introduction to the main problems of the security and privacy of machine learning. As I told, I'm working at the Budapest University of Technology and Economics, and within that, in a laboratory which is called CrySyS. My colleagues are quite well known about discovering different malwares in the wild. And I'm working particularly on the privacy side and the privacy and security of machine learning. So this is a small lab. There are 5-6 permanent researchers and a couple of postdocs, not a big lab. Still are trying to do some interesting stuff. So this talk is about the security and privacy of machine learning. At the beginning, it's very important to distinguish two main fields or topics. One is when we use machine learning to solve security problems. And this talk is not really about this. So this is really about the security and privacy problems of machine learning. However, similarly to like any other secure system, we can group these problems into 3 main categories: confidentiality, integrity, and availability. Some of you might have heard of this categorization. It's very famous, widely used in industries. And they are trying to focus on different problems of security problems. So this is which I decided to present you in the context of machine learning. So let's start with the first, which is confidentiality. So what is confidentiality? In confidentiality, with regards to machine learning, we can distinguish 2 main problems. One is when we are interested that if we have a machine learning model which of course does some predictions, and we as an adversary, we can access only the output of this model, so the prediction results. Can we deduce the training data from this output from the predictions? So if we can only access how, for example, a model classifies certain people, can we know or learn what people were exactly included in the training data of the machine learning model? Of course, it's an important question, because if you imagine that we have a hospital, the hospital trains the model, and the output of the model, for example, is that which cancer the patient has. So if we know that a particular person was in the training data of the machine learning model, then we will learn that he has or she has cancer. So basically, the machine learning model itself, the output only, can be used to deduce the information, and because of that, it can regard it as a personal data. So the machine learning model, which is shared maybe by the hospital with other hospitals or organizations, they have to be very careful, because if this holds, then GDPR applies, and the hospital has to follow the obligations of the GDPR. Now the question is that why is it possible? So if we only have access to some aggregated data like the predictions, which are typically probabilities or confidence values, why we can learn that someone is included in the dataset? And the reason is that many machine learning models like neural networks, they have tons of parameters, so they are very complex. Sometimes they have more parameters than training data. So they can fit very well to one particular training data point. For example, if you have an outlier in the training data, and this outlier is a bit different from other training samples, then there are techniques which can be used to extract this outlier from the machine learning model. So I prepared an example for you, just for illustration, and this is a malware classification with machine learning. So in malware classification, we have a binary code, and we want to know whether this code is malware or benign. So it's a kind of virus or a benign program. There are machine learning solutions to do this. Basically, they are checking different features of the binary. For example, what kind of assembly instructions there are. If there are some typical instructions for the malware, then they can distinguish the malwares from the benign. So in this picture, what you can see, we have malwares and benign samples in the training data. We just consider two features, X, Y axis, and we want to know whether we can separate the two groups of samples. What we are doing is trying to find a separation curve or decision boundary, and this decision boundary separates these points of samples. And what is on one side of the decision boundary will belong to the one group and the other is the other. So if we can separate them very clearly, then our classifier will work very well. Now the problem is that if you have a huge model, then it will explicitly memorize outliers, which are harder to learn. So they create a separate decision boundary from them. They are memorized by the parameters, and they are more easier to extract them from the output of the model. Now I will not detail how to do it, but you can get the intuition now why it's working. So these kind of attacks, which tries to extract this information, it's called membership attack, and it's widely used in auditing machine learning model to be GDPR compliant. Now the other problem is integrity, and this is a bit wider. So integrity is really about how we can attack the machine learning model. So we have an adversary, and we have a machine learning pipeline. So in the pipeline, as you can imagine, first we feed the model with the training data, then with the learning algorithm, we create a machine learning model. So we compute the parameters of the model, and after that, we can use this trained model to perform some inference, for example, a malware classification. Now, the adversary have two main choices to influence this model. The first is that he manipulates the training data, which is called poisoning attacks. So maybe he crafts some training samples, puts it into the training data of the machine learning model, and then tries to influence the decision of the model. And the other is that he performs attack on the already trained model. So the training has happened, and after that it's applied in a real in real application, and then the adversary crafts some examples, which are called adversary examples, to fool the machine learning model. So it adds some well-calibrated noise, which are not visible for human, but still it will totally misguide the model, and it will misclassify the sample. So I will detail what I mean exactly by these attacks. So the first is this is the evasion attack, when we attack the model in the testing phase. So when we apply the already trained model in the real application, and the adversary examples are created by adding some invisible noise to the training sample. So by invisible, I mean that they are not perceptible. So if we have an image recognition system and we add some noise to the picture, and after that the noisy picture will be misclassified the model. So this is a peak, and it remains a peak for a human, but for a machine learning model with the noise, it will classify as an airliner. And this is very, very easy to create such examples. So why is it dangerous in reality? Because usually we don't want to classify pigs. But if you imagine that we have a self-driving car which takes pictures of the road and it makes decisions based on these pictures, then now if there is an adversary somehow in this pipeline and can manipulate the pixels of this or the image, the pixels of the image, maybe it can change just a single pixel in order to cause some misclassification. For example, if there is a road sign on the image, which is a stop sign, and because of the manipulated pixel, the machine learning model will recognize it as a yield sign, so it can cause accidents basically. And in fact, it can happen even in a natural environment. So when you have a car and then the lighting is different from normal, and it will decide to take a wrong turn on the road because of that. So it can has really safety implications of this kind of attacks, and that's why it's very important to defend against that. So what's the reason of that? If you know about neural networks, you know that each neuron makes an elementary decision based on its input. And the problem is that even if we just very negligibly modify a single input, like a single pixel, in total, the linear combination of the pixel can exceed a certain threshold, which may change the behavior of the neuron. So even if the modification of each individual pixel is very small, in total, the decision is taken on the aggregate, and this aggregate can change by a lot, and this can change the decision. So here, if you have a decision boundary, again, the samples which are close to the decision boundary, they can be shifted to the other side of decision boundary, thereby changing the decision of this sample. So this is how we can actually have a malware, and we modify the malware so that the malware detector will recognize it as a benign sample. So why? Because sometimes malware has some features in the binary which we can change arbitrarily. So if we have a executable code, usually some parts of the executable code do not influence the logic of the malware. So there are some payload in the binary file which we can arbitrarily modify without changing the operation of the malware. But since we can change it, it can influence some features which are used by the malware, and hence we can manipulate the decision of the malware detector. Yes, for example, some malware detectors can be easily fooled by just appending a large benign payload to the malware sample, and it's enough to fool them. And it's very easy to do. So now the second attack is that when the adversary tries to poison the training data of our machine learning model, this is somehow easy to imagine that it can be carried out because the training data sometimes come from untrusted sources. For example, in case of machine learning, in case of malware detection, the malware samples are typically collected from untrusted sources, so we don't know where it originates from. Maybe it's coming from an adversary who's trying to manipulate the training sample. So we distinguish two types of poisoning. One is the targeted poisoning, and the other is the untargeted. In case of the targeted poisoning, the goal of the adversary is just to misclassify a single sample when the machine learning is used in a real application. So we have this plot again. We have the decision boundary, which is normally learned by the machine learning model. And now we have a target sample, so it's targeted by the adversary, and the adversary wants this sample to be misclassified as benign. So what it can do is that it injects a new sample in the training data, which is labeled as poison, and it creates the sample so that the features of this sample is very close to the target sample, but it has a different label. So again, it's inserted in the training phase, and after that, the training happens. So what happens? That the training data, the machine learning model will find a different decision boundary so that it adjusts to maximize the classification. And as a result, the target samples will be fall on the other side of the decision boundary, and it will be classified as benign. So basically, if we pollute with benign samples around the target sample, then we can achieve this targeted misclassification. There are different optimization problems to do this, and now I will not detail this, but you can get, again, the intuition. So in practice, why it's dangerous, this kind of targeted poisoning? For example, in recommendation system, if we can manipulate the training data of a recommendation system, then we can alter the ranking of different products. So we can put some products in a higher rank, and it will be shown to the user. And thereby we can maliciously advertise some products. Or speech recognition system. In speech recognition system, the pronounced words are digitalized by machine learning algorithm. And actually, this is also trained on real pronunciations or utterances. And if we just inject some malicious samples, then we can cause misclassification of some digit. And what is important that it's enough only to inject a very small amount of data. Like if we have the training data set in these specific examples, which was carried by some other researchers, they shown that only 0.1% of the training data is, if only this percentage is polluted, then we can already achieve this misclassification. And finally, federated learning. In federated learning, a lot of clients, or basically companies, institutions, they build a common model in order to benefit from each other's training data. And since they sometimes not trust it, they can also change the training data, thereby polluting the common model, which is after that shared with all the companies. The other attack, which is also poisoning, it's called untargeted attack. Unlike to the previous one, here the goal of the adversary is to cause an overall to degrade the overall performance of the machine learning model. So not only on one particular sample, but on as many samples as possible, or better to say, in as many classes as possible. So basically, we get a model which on average has very low prediction accuracy. So what we have now, normally also we have this decision boundary, and the adversary wants to modify this decision boundary. So it injects some poisoning samples in the training data, which are scattered in the space. And what it can do is basically just relabeling some benign sample as malware samples, which will cause the machine learning model to find a different decision boundary. And as you can see, this decision boundary is much more complex. And because of that, first, it takes more time to learn this, so it will prolong the training, which is not really good in certain situations. And the other is that the accuracy will be decreased, because as you can see, some benign samples will be misclassified as malwares. So this kind of attack is really about degrading the overall performance of the machine learning model. So why is it not good? In practice, there can be applications where this is a problem. The first application, for example, is if we talk about fairness. Let's say we have this application called the recidivism prediction. So we want to predict whether a prisoner will be, if he is released, whether he will commit a crime again or not. And for that, they have already used machine learning models to predict this recidivism. And here, if we relabel some, for example, some black people as criminals, then we can increase the chance that black people will be labeled or predicted as criminals by this model. So basically, we can cause some kind of artificial fairness problem in this machine learning model through this attack. The other is that the cloud services. So you know that many companies, they train the machine learning model on cloud services, for example, on Amazon, and they pay for that. So if you use these services, the more, I mean by time, then as the time increases, the usage time, you pay proportionally more. So if the training time is increased, then you have to pay more. So this is an attack which can actually increase the cost of the company, the training cost. And finally, backdoors. This is a special kind of integrity problem, very related to poisoning, but not exactly the same. So just to imagine the intuition of backdoors, actually it exploits a very interesting phenomenon in machine learning. The fact that sometimes machine learning is not explainable, and we don't know why it makes a certain decision. And sometimes it bases the decision on features that we don't want to consider. For example, in this application, the task was to distinguish wolves and huskies, which is a kind of dog. And the model worked pretty well, but when there was a husky, it was misclassified. And the reason it turned out was that the model recognized the background and made the decision on the background, which was snowy. So if there was snow, the model know that it's probably belongs to wolves, because all the pictures with wolves had snow in the background. So it didn't recognize the features of the animal itself, but just the background. And this behavior can be exploited with a backdoor attack. So how, if we have a malware detection system, what the adversary can do is to create some kind of artificial feature and to inject it each benign sample, training sample. And this is present in every benign sample. So what happens is that the model detector will recognize benign sample, distinguish malware samples and benign sample based on this special feature, which is a special bit string in these examples, like the last 4 digits. So if this last 4-bit sample is present in the benign sample, in all benign sample, then the learning model will know that, okay, if we have this special sample, then I will know that it's a benign sample and I will decide it based on the benign sample. So again, it will not consider any malware features. It's just this checking the existence of this pattern. So this special pattern, which is present in each benign sample, it's called the trigger or the backdoor. So what happens after that is that when this backdoored machine learning model is deployed in the real application, then the adversary creates a malware and it injects this special backdoor sample to the malware. So it appends this bit string to the end of the malware, which doesn't influence the logic of the malware. This is possible, I told you. And after that, what happens is that the model checks the existence of this trigger, this pattern, and it will learn that it's a benign sample. So basically, we can fool the machine learning model with this attack. Again, this is an attack in the training phase. So we have to inject this backdoor into all benign samples in order to make this attack work. So yeah, this is what I told you. These attacks are realistic because the training data sometimes comes from untrusted sources. For example, in case of malware, it's collected from the malwares from the intelligence network, and we don't know how they are manipulated by the adversary. So the last problem category, is called the availability. It's pretty new and very interesting problem. So the availability problem pops up when the machine learning model is not available. For example, it spends too much time on making a certain classification, and because of that, it cannot be really applied in real time in real-time environments with real-time requirements. For example, if you imagine we have a self-driving car, there is a picture, the car has to make a decision immediately, for example, to make an immediate maneuver. And if there is some delay, it can really cause accidents in the roads. The other is that if we have the IoT devices, nowadays they also deploy machine learning models to IoT devices. They are resource constrained, so they sometimes are operated from batteries. And if the model takes more energy because it needs more computation, then it can deplete the energy much faster. So basically what we are looking for, or what the adversary wants to do, is to find some samples, testing samples, so it's in the testing phase, in the already machine learning model, to create some sponge examples which takes more computation from the model. So the model needs more computation to arrive to the final prediction of this sample. And actually, it's possible to artificially construct some examples, even if we can only black box access the machine learning model. So we don't access the parameters of the model, just the output of the model, the prediction, and we actually can use some genetic algorithms to find gradually a sample which maximizes the response time of the machine learning model. So this is also possible. It has been shown 1 year ago, so it's a pretty fresh result. Okay, and the defense is, well, I will not detail too much the differences. What is important to remember that almost all the differences are trade-offs. So there is no perfect defenses which provides perfect security. There is always some kind of loss of utility. For example, degraded accuracy at the cost of security, or a bit longer response time. It really depends on the problem. There are a lot of different countermeasures, but it's important to keep in mind that there is no free lunch. So finally, the conclusion is that privacy and security are very important because we have to build trust. So people will use some system if they trust it, if they know that it cannot be attacked. And the other is that these machine learning models, which I showed, it's very easy to attack. So they are very vulnerable to attacks because the machine learning pipeline, so from the collection of the data till the design of the algorithm, there are a lot of points where the adversary can access the pipeline and do some kind of bad things, nasty things. And finally, the security and privacy of the machine learning models are the audit of this security are mandated by different regulations. So actually, the companies need to. It's compulsory to audit the machine learning models, and probably they need a lot of experts. So that's why it's really, I think, a good idea to study this kind of fields, and there is a lot of market for such kind of people. So this is that I wanted to talk about. If you have any questions, just please ask. I'm happy to answer.
Perfect. I think, thank you very much, Gergely. This was wonderful. I think, especially, I really like the sponge tactic. Well, I was thinking myself, I mean, it's not unusual to have the huskies with snow background, because as you know, that in the tundras, people do use huskies to actually take them all over the place, right? They are like armies. You know, you'll have 20, 30 huskies pulling the sleigh and taking these guys in the North Pole and also in the South Pole. So definitely, I think how humans are sort of, you know, how our vision system works versus how a computer vision system works is entirely different. And you can map so many features. So I think from this perspective, I guess my question to you would be how to automate and create software that allows us to not slow down, because a lot of people say security, privacy, it slows everything down. We don't want it. We don't want that. We just want to be very quickly be able to use the machine learning systems into production. Is there a way we can design systems that have these that do the continual learning, the lifelong learning aspects into, and putting security and privacy into concern? Do you think there's going to be software development in the coming in the future, or is there already software?
I think there is one notion which is very important. It's called security and privacy by design. So a lot of people think that security is only important if there is some attack and then we patch the system. So it doesn't matter. It's about machine learning or security or other systems, information systems. But it's much more important to prepare for the attacks and to design already from the very beginning the system with security in mind. So even in machine learning, for example, some attacks can be circumvented by special training algorithms which prepare for these attacks. It has some cost. For example, a bit it degrades the accuracy, and there is a substantial research to make this trade-off more appealing, so to make it more secure and more accurate. But this is really a active research area. It seems now that most defenses they have this trade-off and we cannot avoid. But the amount of trade-off, so how much we sacrifice accuracy or
Speed of deployment,
speed,
etc.,
it
passing
really
through the governance and privacy filters, security
depends.
officer saying, "Hang on," all those. That's what I also mean. And not a technical slowdown, but also humans in the loop will slow it down. That's why a lot of software companies hate the fact
Yeah.
to put too much of all that.
Yeah, it's very important to understand that it's always about risks. So when there is an attack, it has an impact, and you can measure the risk. And when there is a mitigation, like countermeasures, it has also some impact, and you have to balance them. So you have to check if it mitigates the risk. And overall, if I apply the mitigation, maybe I have a less accurate model, but still I avoid something which, if happened, could cause a much larger loss to the company. So this is always about risk analysis, and it's very important. And actually, the regulations also suggest to follow this kind of risk-based approach.
Final question, Gergely. I know you'll be teaching. You're one of the faculty members. I know you already started teaching the Human-Centered AI Masters. I know it's coming into fruition. What is the advice that you are giving students while you're teaching right now? What should they be learning, and how should they be learning? And why is such a Human-Centered AI Masters, an ethical masters, more? I don't know. I wouldn't say more useful. I would say equally useful as learning the technology. What is your advice to the students?
Um Yeah, I mean, what is important is to consider the human aspects. So, for example, in terms of security, trust is something which is very human related, and one has to understand very well that people can be really influenced by trust. So if we design systems, secure system, actually we build trust in customers, and this is the main human aspect of security, and thereby we can enforce the application of these systems. And the related technologies, these countermeasures, they can. So basically, we will start a course next semester about the security and privacy and machine learning, and we are trying to make some kind of exercises, laboratory exercises, how to use this kind of security countermeasure. But it's very important to understand this risk-based approach that I was talking about just a few minutes ago. That when you apply a countermeasure, it doesn't mean that it will suit the company needs. So you have to understand that it's always about balancing the risk and the utility loss and the benefit of the security countermeasures. So you need a risk-based approach. You have to probably learn about risk assessment. It's very important for security, even in the industry. You have to learn technicalities like how to train machine learning model in a robust way, and you have to understand the risk. So this is this course about that what different risk attacks there can be, and just to learn this mindset that how you can design such kind of attacks.
Wonderful. Gergely, we are running out of time. Thank you so much for this wonderful presentation. I really appreciate it, and I look forward to meeting you soon. I believe we have a physical meeting set up in the end of May. We're very excited to be in Budapest to actually sort of learn from each other. Just to the audience as well, you can connect to Professor Gergely as well. It doesn't matter. You can just connect to him on LinkedIn, and if you have any specific questions regarding his expertise, reach out. If you have any questions specifically around Human-Centered Masters, AI Masters, do reach out to us. Just click on the link. I just shared the link of our website as well. Make sure that you are participating in it. If you are, make sure you're talking to these universities and making sure whatever arrangements that need to be taken. Thanks everybody for this wonderful start of this Meet the Instructor series, and happy to have Gergely kick starting this or kicking it off, which is wonderful. So thank you so much, everybody. Gergely, I want to thank you as well. Have a wonderful day, and I'll talk to you, all of you guys, soon. Take care, and bye-bye.
Thank you. Bye-bye.